Hello Primary 6 from Qifa Primary School. Welcome back to a continuation from previous lessons. For this lesson of physical chemistry, we'll be classifying 9 different types of solutions. So we have the different categories over here. The ABC is the cases for each condition, the different cases for each condition above. In the above is basically of the basis of different conditions, and as there are different conditions like the ideal, whether it is ideal or not, whether H2O is its solvent or not, and all those. Okay, so for the first one, what we'll have is ideal and non-ideal. So ideal is that what we'll want from an experiment, like what kind of results would you want and what do you want from an experiment after the solution, after you get the solution. Well, the second one is basically whether H2O is the solvent. The third one is to see how much solvent there is. And the last one is the amount of solute. So for all of these, when we are considering each condition, we aren't going to consider the others, okay? And so it's like how the amount of solvent affects concentration and dilute and whatsoever. Okay, so let's start with the first one, ideal. So ideal is going to be what we want, right? So ideal is that it will obey Raoult's law. So it will obey Raoult's law. So what is the Raoult's law? So Raoult's law is basically the solvent in gas state, the pressure from the solvent in gas state. Okay. So to put it simply, the formula is P solution is equals to chi. So this is not X, this is chi, okay? Chi P, wait, let me just rewrite it. So it is P solution is equals to chi P solvent. So this is the Raoult's law, the pressure from the gas state of the solvent. But over here, if you only have one region of the solution and obeying Raoult's law, it is still not the ideal case. So it has to be in every range of concentration and temperature. Both concentration and temperature are going to be important. Well, for the second one, what we have is the fact that the intermolecular force is equal. The intermolecular force is equal or almost equal. So for this part, it's basically saying that the ideal case over here, so there must be two first, okay? It means that, so over here for this part, imagine this is the solution before the diffusion happens. whereas there's going to be a barrier here, and then over here is solution A and solution B, and here is a barrier. So at first the solution is going to be like high intermolecular force. What it means is the force between two molecules. Well, if you're wondering why if you switch the E with the R, that's very different than intramolecular force, which is the force within the molecule. But since we're talking about intermolecular force, it's between two molecules. So over here, molecules from solution A will only be with molecules from solution, will only have a force in between with the molecules from solution A, and same with the molecules from solution B at first. Then after that, after the diffusion happens, once the barrier is removed, after all of that happens, the intermolecular force is going to be equal, almost equal, whereas A is going to have the force with B, and or reverse also can. Well, for non-ideal, what we have first is, first and foremost, does not obey Raoult's law. Even in every region except for one doesn't obey the Raoult's law, it will not. Well, the second one is that both negative deviation and positive deviation are not non-ideal, because if it is ideal, it will be equal. So for non-ideal, it's either, as long as one condition is not met, it is not ideal. But the first one is that it does not obey Raoult's law. And the second one is either negative deviation or positive deviation. Whereas ideal, it needs to be both obeying the Raoult's law in every range of concentration and temperature, and the intermolecular force is equal. There is no positive or negative deviation. So now over here, just take a quick look before I erase it. So this part above is the formula for the Raoult's law, and remember this is not X, it's chi. While below is about the intermolecular force in the ideal case. So take a quick look and okay, so now it's aqueous and non-aqueous. So over here we're going to see the amount of H2O as solvent. So this is going to be more or less obvious, the fact that over here is basically seeing, because for like a lot of experiments we use water as a base and all, not because that we only do experiments using water as a solvent, but it is easier to convert to the others, and when water is the solvent at first. Okay, so the first one is obviously water. The water is not the solvent. Water is. H2O is the solvent, and over here we have a few examples, so to be specific to. The first one is sugar in water. Yes, sugar dissolves in water. Sugar in water. Yeah, just you just mix sugar and water together. Then the next one is carbon dioxide. You can just write this as H2O if you want. Both are fine. So sugar and H2O, you can say any kind. Then after that, it is carbon dioxide and H2O. It's like something a bit like those carbonated drinks and all, whereas there is carbon dioxide in the water. And the second one is most definitely the solvent is not H2O. An example. The first example is carbon disulfide. Which is CS2. Okay. Wow. The second one is violated liquid. So, it is CS2 and the violated. Oh, I mean volatile. Sorry. So, volatile liquid. Yeah. There. Sorry for the spelling mistake. Then the next one is the amount of solvent and how it can affect like how concentrated dilute the solution is. So first is there is a small amount of solvent. Very pretty obvious, or in other words, it will be there is a large amount of solute. Both are pretty much the same thing, whereas small amount of solvent and large amount of solute, because and when we're saying small amount is like when you're comparing. So over here we have a few examples, whereas so concentrated is that over here for this part comparing to dilute, there is a smaller amount of solvent and a larger amount of solute. Okay, so over here for this part, the first one that we have is orange juice. The solvent is acid, so there is not going to be that much acid. I mean, if you have too much acid in your drink, that's also not good, okay? So, for this part, the second one is dark colored tea. So, it can be any dark colored tea, but the important part is like it is dark colored tea. So, it's a dark color to know that it is concentrated, and instead of just like a certain type of tea, it's like the color of it is showing how concentrated it is. While the second one, dilute, there is a large amount of solvent. So examples. First one we have salt in water. So over here when I say salt in water is that you can actually control how much salt there is. So what I'm saying about this is that there's not that much salt in water. We're not talking about some salt overdose in the water, whereas it starts tasting like seawater and all those, whereas you cannot drink it and all. It's just a bit of salt in water, okay? Well, the second one is light colored tea. Assuming that these two tea types are the same, and depending on how diluted or concentrated it is, the color would be different. Okay? So over here, this is what we have for amount of solvent. Then as for amount of solute, we have 3 instead of 2 cases compared to all of these. So the first one, non-saturated. Saturated, then supersaturated. So what is non-saturated? More solute can be added to the solvent without creating excess and when I say excess solute, I will explain it as supersaturated, okay? So for this right, it's very diluted. Well, these two can be related together, but it's still not completely the same, because the way we are saying about this is that over here it's more or less like the proportions, saying that if there is like a small amount of solvent, large amount of solvent, large amount of solute, small amount of solute. Well, this one is that can you add any more solute to the solvent, the solution? Well, or is it that you cannot add any more solute without creating excess solute? Or it already has excess solute, which obviously you cannot add more. So for saturated, as I already somewhat explained it earlier, is that no more solute can be added solute can be added to the solvent at the same temperature. So no more solute can be added to the solvent, or else it's going to be excess solute, unless you increase the temperature or add pressure, or just mix them not by themselves, but you also have to stir them. So this one over here, because by stirring, heightening the temperature and adding additional pressure, it will actually cause the solute to have more capacity, the solvent to be able to take in more of the solute without creating excess, until you change it back or something like that. So for supersaturated, it is that there is excess solute from the solution and you can only change it unless it was stirred, had additional pressure, or had heightened temperature. Unless it had been stirred, heightened, its temperature had been stirred, had additional pressure, or the temperature was heightened. So over here, as I told you before, by heightening the temperature, adding more pressure, or stirring the solution, it can take in more of the solute. So over here for this part, and what if you decrease the temperature afterwards, after it had gotten it had the additional temperature and all those? Also, what will happen is that the solute will crystallize. And when it crystallizes, the experiment, you can also do it yourself by using salt and adding a lot of salt to the water, then after that having a stream to make it crystallize. And also, if there's like excess solute after it has dissolved, then you lower the temperature, the solute crystallizes. So that will be all for this lesson. Just take a quick look, and thank you for your watching.